Good evening. I'm Spot On Weather meteorologist Matthew Euler, and for tonight's special video, similar to what I was mentioning at the ending of my last teleconnections video, I wanted to really dig into these U.S. seasonal temperature trends. Really, my mind started thinking about things as far as, how many above normal temperature days, especially with the high temperatures, how many above normal days do we typically see during the winter season in the United States, as compared to record cold number of days? Additionally, in this video, I expand out to all seasons and show the ratio of record highs versus record lows, so warmer than normal temperatures versus colder than normal temperatures. It just seems, recently that we're in a period where we're seeing more and more record warmth. And we go back to 2010 alone, and from 2010 to 2020, those particular years, we've seen some of the warmest temperatures on record across the United States, the warmest years on record, as well as at the global scale also. So my mind was just really thinking about things, and I really wanted to delve into this research. So I wanted to do this special video, and especially now as we head towards the winter season across the United States. We're coming up on mid-November, mid to late November period. This is an actual map of the coldest temperatures ever recorded in the United States for each state, showing you the temperature in degrees Fahrenheit of the coldest temperature ever recorded in a specific state. So let's go ahead and get into the discussion. Here's my overview. I wanted to investigate the frequency of above normal versus below normal temperature departures across the United States. That's the main focus of this video. I did throw in a global temperature change slide as well. So I did show a little bit of the global temperature trends, which pretty much mirror the United States trends. I was intrigued to conduct this study based off a trend of more frequent above normal temperature days as compared to below normal temperature days in the recent years. And for example, this is one of the common questions or thoughts that came to my head: how very uncommon it is to have record cold temps in the summer season. I mean, how many times have we seen record cold in the months of June, July, or August, right? Not very often at all. When have we seen record warmth? And in what seasons have we seen that record warmth? We get these heat waves that tend to be more frequent and longer lasting in duration across the United States during the summer season. And we also see the warmth the trend generally looking at winning out over the colder temperatures in the winter season. And so I want to look at how very uncommon it is, my thoughts, to have record cold in the summer season with decreased frequency of record cold in the winter season. So I find that very intriguing. More common to see record warmth not only in the summer season, but also in the winter season, with warm air seeming to be more of a threat to push back colder air. By the way, the data source for a lot of these slides in this presentation are courtesy of the U.S. Environmental Protection Agency. Once I was doing my research, I came across some of these slides that are really excellent to just really show these temperature trends. All right, so let's first take a look at the daily high and low temperature breakdowns. All right, so if we look back at the unusually cold daily winter temperatures, right? For this graphic, we're showing the cold daily highs, the cold daily highs smoothed out, the cold daily lows, and the cold daily lows smoothed out. All right, so we're going to go back in the record to 1911, between 1911 and 2020, and we're going to look at the percent of land area on this graph, bottom left. You see the percent of land area on the y-axis ranging from 0 all the way up to 90. So the higher you go up on the y-axis there, that vertical line there on the far left of the graph, the greater the land area is covered by these cold daily highs and cold daily lows, or unusually cold winter temps. All right, the bottom there, the x-axis, the horizontal area there at the bottom of the graph, shows the years again ranging back to 1911 to 2020. All right, so the main takeaway we get from this slide by just looking at it, right? The higher the spikes in the graph, the greater the land area that's going to be covered by these unusually cold winter temperatures across the United States. So, for example, some of the previous winters where we saw, a larger land area covered by these unusually cold winter temps included right around 1918. You'll see another spike there at 1936, 37 time period in the winter. And then you'll see a really large spike there just prior to 1980. 1979, you see the nice little spike there. It's the tallest spike of the whole graph, actually. But then look at the far right portion of this graphic between 1990 and 2020. And there was a little bit of a spike there in 2010 winter season. But in general, you'll notice if we smooth out these cold daily highs, these cold daily lows, you'll notice a general downward trend in these unusually cold winter temperatures across the United States, a decreasing frequency of unusually cold temperatures, covering a much smaller land area. So these cold winter episodes tend to be less broad and more isolated or concentrated in specific regions of the United States. Let's take a look now and flip this coin over to the unusually hot summer temperatures in the United States, going back again to 1911, from 1911 to 2020, the years. And you'll notice on the bottom right of the graphic here how we're showing greater land areas, the heat being more expansive, covering a larger land areas. From the year 2000 to 2020, you'll see an increased frequency of unusually hot summer temps. And even if we went further back to 1980, we'd see that. Notice that upward trend in unusually hot summer temperatures. So what is this saying? If I just look at these graphics alone at daily temperatures in the United States, what these two charts are telling me, or these two graphics are telling me, number one, that the unusually cold winter temps are becoming less frequent since 1990, and we're having increased frequency of unusually hot summer temps since 1980. So colder air is not, basically the temperatures aren't as cold, and the land areas that they're covering is not as great, and we're seeing an increased frequency again of those hotter temperatures over larger land areas in the United States. If we look at daily record high and low temperatures here, now this graphic goes back to 1950. And it doesn't quite go all the way out to present time in 2021, but I thought it was still an interesting chart to show nonetheless. And so the percent of daily records is generally there on the y-axis, and then you see on the x-axis there you have your decades: 1950s, 1960s, 1970s, 1980s, 1990s, and 2000s. So from this graphic, if you look at, as we go decade by decade, okay, so 1950s, for example, you notice that we had generally the same amount of daily record highs to daily record lows in 1950s, that decade. The 1960s, we actually had a trend towards more record-breaking low, cold temperatures as compared to record highs. The 1970s, pretty much slightly colder time period where we had a greater number of daily record lows as compared to record highs. And the 1980s, now things start warming. You'll notice the red bars there, 1980s, the decade, 1990s decade, and the 2000s for sure. Look at the growth in the vertical of the red bar, which indicates that we have way more record highs than we do record lows. So the overall facts I have listed on the right from this graph. First of all, record-breaking highs are now outnumbering record-breaking lows by an average decadal ratio of 2 to 1. So we're seeing twice as many record-breaking highs as compared to record-breaking lows over the past 20 years. Most decades in the 20th century had close to an even ratio of hot to cold records. And you can see that again in the graph on the left, the 1950s, 1960s, it was slightly colder, more record lows than highs. 1970s was a cold decade as well. But then, since the 1980s, things have really warmed. The 1930s, if we were to look back further in time, the 1930s, by the way, were driven by these Dust Bowl summers. Had about 1.4 hot records for every cold record. So a 1.4 to 1 ratio, hot to cold. And the 1960s and 70s had about 1.5 cold records for every hot record. And the overall 21st century has a 1.9 to 1 hot to cold ratio. So this again is interesting data that's telling us that our temperatures, we're seeing more warmth than cold. Now let's take a look at the seasonal temperature breakdown. I thought this was pretty interesting here. All right, so the average U.S. seasonal temperatures. Now, these graphics for the different seasons extend all the way back to 1896. So 1896 to 2020. And you'll notice these are temperature anomaly graphics, by the way, in degrees Fahrenheit. So the values on each of the seasonal graphics here, -6 to +6 on the y-axis, those are your temperature anomalies in degrees Fahrenheit. So let's take a look at each of these particular seasonal breakdowns. And by the way, before I do that, I wanted to clarify the winter season is the months of December, January, and February. The spring season is the months of March, April, May. The summer season, June, July, and August. And the fall season is September, October, and November. Okay. Now, if you look at winter in the far upper left graphic there, have you noticed something very striking here? It is how much above normal these temperature anomalies are becoming. If you notice there, just around the year 2020, we were sitting at about 3.8, 3.9 degrees Fahrenheit above normal for the winter season across the United States. But the overall trend of the winter graphs, you go back to the late 1800s, into the early 1900s. There were some warm and cold periods in there, all the way up through pretty much 1979. That was really a very cold winter across the United States, where, the seasonal mean temperature was almost 6 degrees Fahrenheit below normal in 1979. But then you notice the upward trend and these spikes on the winter graphic there on the left for the winter season, and how much more on the positive side or above normal those winter temperature anomalies are becoming. Spring is in the upper right. So with spring, we did have one major spike there in, it looks like 2011, 2012 time period for spring season, where the temperatures were up to 5 degrees Fahrenheit above normal. But again, that trend for spring season is also trending above normal. Summer season, the bottom left, generally showing we had some cooler summers back in between 1910 and 1920, it looks like. And then we had some warmer summers, some hotter summers there during the Dust Bowl era in the 1930s, especially the middle to late 1930s. And then we had a drop-off again around 1950 for the summer season. Temperatures were almost 2 degrees Fahrenheit below normal for the summer season. And then things kind of leveled out until we reached basically the year, it looks like about 2005, if I'm interpolating this, using interpolation. And generally we have an upward trend in the departures from normal, up to 2 degrees Fahrenheit above normal in 2020 for the summer season. And then the fall's in the bottom right. And that generally shows a fairly consistent trend. We did see a few anomalously warmer fall seasons, especially back in the early 1960s. And then we had an anomalously cool fall season back in the about 1976 time period before things kind of came back up. And then if you look generally around the year 2015-16, fall season was almost 4 degrees Fahrenheit above normal across the United States. So overall, these are really interesting graphics to kind of show you the trends in the temperatures for the different seasons in the United States. The main takeaways here are winter is the most vulnerable to the rising temperatures. And, this backed up my thought completely about what I've observed. In general, with the winter seasons tending to become warmer and warmer with each passing year. The overall average temperature, I'm not saying you can't get those cold periods, because those still do occur. But are the colder periods shorter in duration now? Are the temperatures not as cold as they once were back, let's say, 30, 40 years ago? So in general, this graph here describes it. Winters most vulnerable to rising temperatures. We're seeing warmer winters. Overall, the minimum temperatures, those low temperatures overnight into the early morning, have actually increased at a higher rate than the average maximum or high temperatures for the day. So we're getting minimum temperatures that are not dropping as low at night. Most of the warming in the U.S., by the way, has occurred during winter nights, when it should be the coldest time of day. So I found that very interesting as well. We look at changes in seasonal temperature by state, going back to 1896, and you'll notice the largest seasonal temperature increases are indicated by the maroons, the darker red coloring on these seasonal breakdowns for the U.S. You'll notice that in the wintertime, the upper left-hand graphic there. Look at the warmth across New England. Look at the warmth, the red and the maroon shadings across the upper Midwest, Michigan, Wisconsin, Minnesota, South Dakota. Look at North Dakota. That has the largest seasonal temperature increase between North Dakota and Maine. Two of the largest temperature increases for the winter season as far as temperatures go. And there's really not much change in the winter season across parts of Arkansas, the Deep South, Louisiana, Mississippi, and Alabama. But overall in the U.S., conditions are warming. They're warming each winter. The graphic in the upper right shows spring season. And with the spring season, the temperature increases aren't as great as they are compared to the winter season, especially for the northern plain states. Summer season, we actually have a cooler summer seasons across the southeastern U.S., across parts of Kentucky, Tennessee, Mississippi, Alabama, Georgia, as well as Arkansas, Missouri. And the temperatures are warming across the western U.S. in general, in the Four Corners region during the summer season. And in the fall season, it's also a fairly cool time of year across the Deep South again, in parts of Oklahoma and Arkansas, Missouri, Kentucky, Tennessee, Mississippi, and Alabama. We're seeing smaller temperature increases in general in the seasons in the South and the southeastern U.S. So our greatest changes in seasonal temperatures by state are occurring at the northern latitudes, especially in the winter season. Those colder winters just aren't happening as frequently now across places like Montana, the Dakotas, and like I mentioned, Minnesota, Michigan, Wisconsin, up in Pennsylvania, New York State, Vermont, New Hampshire, Massachusetts, on up to Maine. We look at temperature changes by season across the U.S., again going back to 1896, and you'll notice that the winter season, we're seeing a total change in temperatures on the order of 2.7 degrees Fahrenheit above normal or warmer than normal. We're seeing an increase there in winter. That's the season that has the greatest increase. Second most increase occurs during the spring, just below 2 degrees Fahrenheit, total change in temperature. And then you have summer and fall following those two seasons. So in general, since 1896, the average winter temperatures across the contiguous 48 states, the United States, have increased by nearly 3 degrees Fahrenheit in the winter season. So, if you're saying to yourself some winters recently, yeah, where's winter? This is mild out here. These temperatures are very much warmer than normal a lot of the time in the winter season. You're not crazy. You're actually right on. Spring temperatures have increased by 2 degrees Fahrenheit, and then the summer and fall temperatures have increased by about 1.4 degrees Fahrenheit in those respective seasons. So warmer winters are consistent with observed reductions in snowfall, and then shorter ice seasons. So I like to think of this is the coupling between the Earth's surface and the overlying atmosphere. So if we have warmer winters, we just don't have the snowpack that we used to have in the United States. And without that snowpack, that tends to reflect the incoming solar radiation and tends to reflect the incoming solar radiation from the sun back out towards space. And therefore, with no snowpack, no high albedo or reflectivity of the snow cover, that energy is able to more readily heat the land without the snow cover. So in general, shorter ice seasons, especially in the Great Lakes region. We talk about the Great Lakes, we talk about lake effect snows in the winter season. These ice seasons are becoming shorter. In addition, warmer winter, spring, and fall temps are consistent with a longer growing season. And I haven't even got into the fact that for poor allergy sufferers out there, that the plants are, allergies are more persistent throughout the year now. The allergy seasons are lasting longer because the temperatures are warming, especially in the winter season, when typically, you'd have that cold air come in and the plants would go through a dormant cycle. But that's not happening as much now. We're shortening the winter season, so therefore these plants remain fairly active and release various pollens into the air. And then I also haven't even mentioned airborne diseases with specific insects that are, still hanging around in times of the year or seasons that you wouldn't expect them to based on the warming temperatures. So a lot of implications with warmer seasons, with this increase in these temperature changes and towards warmer seasons. If we look at winter season, that is warming the winter season overall is warming the fastest. This is data, by the way, is courtesy of the Climate Central. This is a great website, by the way, if you want to check it out. Just Google Climate Central. They have a lot of fascinating articles and graphics on their site. But in general, since 1970 there on the left, look at the orange coloring. That darker orange coloring, the lighter orange coloring, that indicates warming temperatures during the winter season. And if you're looking at, this is degrees Fahrenheit, by the way, so in general, the Midwest, the upper Midwest, New England, your winters are warming. Since 1970, they're now 3.5 degrees to possibly up to 5 degrees Fahrenheit warmer than what it was in 1970 in the winter. That's just astonishing, the rate of warming there. The graphic on the right shows the fastest warming season, so we compare the seasons. And for a large chunk of the United States, we go east of the Rocky Mountains to the East Coast, down to the Gulf Coast, to the Great Lakes. It doesn't matter, that light blue shading on the graphic on the right shows that winter is the fastest warming season out of all of them. Now, in the desert Southwest, into parts of Nevada, Utah, and California, spring is actually the fastest warming season. And in the Pacific Northwest, summer seasons are the fastest warming seasons in Washington and Oregon. So there are some changeable, depending on where you are in geography, that really dictates which season is warming the fastest in the United States. But if you look at the blue shading, wow, winter seems to be for the majority of the United States. Here are the winter season warming impacts. This is winter snowfall trends. And as I mentioned, with warming temperatures now, you get less solid precipitation. You get more liquid precipitation, more rain. So now you do no longer have that snowpack to act as a refrigerant to the overlying air, as well as snow being a highly reflective substance on the ground with high albedo. You no longer have that. So these snowfall trends, the warming temperatures, are decreasing on the order of 46% overall in the United States. Blue dots on this graphic indicate increasing snowfall trends, and then the red dots indicate decreasing snowfall trends. So if you want to take a look at your specific location, where you're watching us in the United States, you can kind of get a feel whether the snowfall trends are increasing or decreasing recently. And by the way, this period of analysis goes back to December of 1969. Okay, so quite some time into the past, and how these trends have changed. Now, let's take a look at the summer season. Let's take a look at the U.S. heat waves. And, this past summer season in 2021, there was a crazy heat wave that occurred in the Pacific Northwest, Oregon, Washington State, on up into British Columbia. The hottest temperatures on record in parts of Canada, out of all places. Let's take a look at the heat wave data. Now, we go back to 1961 with the heat wave data information here. And we're breaking it down into 4 graphics. We have heat wave frequency on the upper left, heat wave duration, the upper right. Lower left, we have heat wave season, how long it's going. and then heat wave intensity in the lower right. So the data was analyzed for 50 metropolitan areas in the United States, and it generally shows, if you look at these bars by decade, the first graphic for frequency, upper left, shows the average number of heat waves per year. And now it has gone from 2 heat waves per year in the 1960s and has continually increased in frequency to six heat waves per year now in the United States in the 2010s. The duration is also increasing. If you look at the duration, average length of individual heat waves in days, these heat waves are now lasting on the order of 4 days, whereas back in 1960s, in that decade, they were lasting on the order of 3 days. Bottom left, heat wave season, average length of the annual heat wave season days, increasing now up almost to 70 in the 2010s, in that decade, compared to just above 20 in the 1960s. And then the heat wave intensity in the bottom right shows average temperature above the local threshold during heat waves in degrees Fahrenheit, almost up to 2.5 now in the 2010s, when it was 2.0 in the 1960s. So overall, you can see which way we're going with this, especially with frequency in the upper left. That shows a strong relationship from the 1960s to the 2010s. Wow, from 2 to 6 for that average number of heat waves per year. So the number of heat waves are increasing. These heat waves are becoming overall more frequent, longer lasting in duration, with greater intensity. Looking at more heat wave data here, going back to 1961, just generally showing these dots on these maps of the U.S. generally represent the changes in the number of heat waves per year. You see the orange or the reddish dots, that indicates that there's an increase in these parameters. And it kind of shows you the different parts of the country that are experiencing these increases with the red dots. So heat wave duration generally extending from the southern U.S. up the East Coast. Heat wave seasons covering, from Southern California along the Interstate 10 corridor, across Arizona, New Mexico, Texas, on up into the Midwest, Mid-Atlantic, and New England, and the heat wave intensity also increasing, ironically, across parts that normally wouldn't get it, lower Michigan, Ohio. So overall, the heat waves are occurring more often than they used to in these major cities across the U.S. Frequency has increased steadily from an average of 2 heat waves per year during the 1960s decade to 6 per year during the 2010s. In recent years, the average heat wave in major U.S. urban areas has been about 4 days long, 1 day longer than the average heat wave in the 1960s, and heat waves have become, again, more intense over time, as we've looked at. Now let's take a look at both U.S. and global temperatures. For the U.S., the average U.S. surface temperatures, this goes back to 1901. So 1901 to 2020 is a period of consideration here. Generally showing these red bars show the Earth's surface temperature, and these are temperature anomalies in degrees Fahrenheit. So we go all the way back to 1901. See those blue bars there between 1900 and 1910. More blue bars between 1910 and 1920. From 1900 to 1920, we had a pretty good run of below normal temperature anomalies. But then, look at the far right portion of this graphic, going back to the late 1980s. From the late 1980s to 2020, look at the preponderance of the red bars on the positive side, warmer than normal temperatures at the surface of the United States. And you see the upward trend in these. So since 1901, the average surface temperature across the contiguous U.S., the 48 states, lower 48, has risen at an average rate of 0.16 degrees Fahrenheit per decade. Average temperatures have risen more quickly since the late 1970s. We've gone from 0.31 to 0.54 degrees Fahrenheit per decade since 1979. And this is the one that really gets me. 8 of the top 10 warmest years on record for the contiguous 48 states have occurred since 1998. 2012 and 2016, by the way, were the two warmest years on record for the U.S. So again, we look at these trends. If we were looking at an overall balancing act or equilibrium, we should see colder periods balanced out by warmer periods, but the frequency is alarming here. I just really am amazed at this data here. Now, if I look at the average worldwide surface temperature, so let's look at it globally now. Look how cold how much below normal the temperature anomalies in degrees Fahrenheit were across the world. The 1900 to 1910, 1910 to 1920, 1920 to 1930, right on into about the mid to late 1930s. We had colder than normal temperature anomalies for the worldwide surface temperatures. Then we had a little bit of a warm period there in the 1940s, followed by a little bit of a cooler period, warmer, cooler. And then from the late 1970s to 2020, you can see the upward trend in those red bars, those vertical bars there in the right-hand portion of the graphic. It's showing that warming. It's very similar to the U.S. trend, right? So overall, worldwide, 2016 was the warmest year on record. 2020, as recent as 2020 last year, that was the second warmest year on record globally. And the 2011 to 2020 period was the warmest decade on record since thermometer-based observations actually began. Global average surface temperatures have risen at an average rate of 0.17 degrees Fahrenheit per decade since 1901. And you would look at that 0.17, oh, that's not much. You would say to yourself, that's not much, that's not a large number. It's not like it's 3 degrees Fahrenheit, right, per decade? But that adds up over time. You get 0.17 degree Fahrenheit rise per decade. Next thing you know, within 3 decades, 30 years, you're looking at about a half a degree Fahrenheit rise. In 6 years, you're looking at a whole degree Fahrenheit rise. This is looking at the average worldwide surface temperature. So we're taking a lot of weather stations into account here. So really impressive to see how this trend has progressed. Here's a rate of temperature change in the United States per century, going back between 1901 and 2020. And in general, you see those maroon shading colors. That's areas of the U.S. that have seen the greatest warming over the last century, with the northern, the western, and Alaska. The northern and western U.S., New England, Alaska have seen temps increase the most. We see decreased temperature change over the south and southeastern U.S. again, and we look at the rate of temperature change per century in the U.S. All right, that wraps things up tonight. I just want to do a quick video, a special video here, showing you how these temperatures have changed. Again, depending on how old you are and the amount of weather you've seen over your lifetime, if you grew up in the 1960s, even the 1970s, it was a very cold period of time in the United States. In fact, one of my past videos, I actually threw some Time magazine covers on one of the videos, on the slides of the video, showing all the headlines about global cooling and Arctic, ice age is coming. Those were some of the headlines in the 1970s on the cover of Time magazine. And now we are seeing just almost like a runaway warming effect, where these temperatures these averages are creeping up. One thing I didn't throw in here were the 1991 to 2020 temperature averages across the U.S. as compared to, let's say, 1981 to 2010, or the previous 30 years to that. If you look at those, and I encourage you to do so, you'll see the changes. The overall averages are increasing and getting warmer, and we're seeing these longer periods of above normal temperatures. You don't see record cold as much as you do record warmth. And that really had me thinking, again, about what's going on. And, I'm not here to debate the why behind the what. I'm just showing you the data that has been pulled and the general trends of these temperatures. And, again, I'm not here to shape your opinion or your views on what's causing this, all right? but I'm just showing you the data and how the temperatures have warmed. Whether we look at the last century, back to 1901, whether we look at the past snowfall trends decreasing, winter season warming the quickest, temperature changes by season across the U.S., changes in seasonal temperature. And this one's really interesting, these graphics here. And just in general, daily record high-low temperatures with daily record highs on the order outnumbering record lows on the average of a 2-to-1, twice as many. We have twice as many occurrences of record-breaking highs as compared to record-breaking lows. And it's just, even locally where we are here in Virginia, I look at these temperature departures each month or even just by day, and you'll get some colder periods, but they're very short-lived. They're very short-lived as compared to the warmer periods. And another thing we're seeing more of is this weather whiplash, where temperatures are going from, temporarily and very briefly below normal to just shooting up to well above normal over shorter time periods. I mean, in Virginia, we can go from, high temperature of 52 degrees in the winter, and then 2 days later, it's like 70. It's like a 20-degree Fahrenheit rise in temperature in just 2 days. And so, again, very intrigued by this. I've been watching and following the weather for quite some time, the temperature trends wherever I've lived. And, fascinating stuff. So I certainly hope you enjoyed this video. I hope you find it interesting. And it will definitely open up your mind to, further research topics yourself, to get out there and do some research on Google and online. We'll be back to do our next teleconnections discussion video in early December. Looking forward to that. There's a lot of interesting weather going on between now and the Thanksgiving holiday, as well as late November. There's a lot of interesting trends recently in the ensemble models that are indicating colder than normal temps across the eastern U.S. Coming up here in late November. And so we're going to have to see how this winter plays out. I'm really intrigued by the teleconnections. I'm always following them closely. All right, that wraps things up. I want to take the time to wish everybody a happy Thanksgiving. Hopefully you're going to have an enjoyable time with friends and family, or maybe just want some downtime over the Thanksgiving holiday. But really, best wishes to you, to your families, and until next time, God bless and take care.